So we just talked about the architecture here, the service sets. Each access point covers one basic service set, and all the access points which are connected to one wired network, we can call them as one extended service set, because that is one LAN. So this is basically, this is part of the same LAN. These two service sets are part of the same LAN. Right? So the extended service set. And so you can call it BSA, the basic service area, and the set of stations is called basic service set, and then the area is called the basic service area. Similarly, you have a extended service area and extended service set, and then the IBSS was the independent basic service set, which is for the ad hoc nodes. All right, and the whole thing is in one distributed system, which is one wired backbone. Now, by the way, I still haven't put on this slide, but here's the point to introduce. So each service set, each extended service set has an ID, and that is called service set ID, SSID. Right? So when you come to a room, you are looking for the name of the wireless network, that is the SSID. Now the frame itself is a little bit more complicated than 802.3 Ethernet frame. First we have 2 bytes of frame control, 2 bytes of frame duration, how long is the frame. Then we have address 1, address 2, address 3, some sequence control, then address 4, and then the information that you want to send, and then we have the CRC, 32-bit CRC. Notice that there are 4 addresses. It's not just source and destination. There are 4 addresses. And so we'll talk about what those 4 addresses are. But first thing is the frame control. Frame control is simply the type of frame, whether it is a management frame, control frame, acknowledgement, what it is. Right? And it also indicates whether it is coming from the distributed systems or it is going to the distributed systems, and so on and so forth. So that is just the frame control. And then the duration, and then the address 1, 2, and 3, and 4, right? So duration can be used either as a duration or it can be used as a connection ID. If it is used as a duration, that indicates the time in microsecond, and if it is a connection ID, then it just tells you what connection we are talking about here, okay, between the stations. Then the sequence control is a 4-bit sequence number for fragmentation reassembly. So if you take a big packet you want to send, you can fragment it and give it the fragment number, and that's what goes here. And there is a 12-bit sequence number for the frames, so it tells you this is packet number 1 and this is the fragment number 1, 2, 3, 4. Okay, so there are 16 bits total. There are 4 addresses, and the thing is that the reason you need 4 addresses is because the receiving and the transmitting station may not be the source or the destination. So here's the thing. There is a wired node that wants to talk to another wired node. However, the path between them goes through a wireless link. They are all in the same LAN. Alright? So the packet will come from the wired node to the access point. The access point will transmit it to the other station. The other station, wireless station. The wireless station will possibly transmit to somebody else, and so on and so forth, right? So that's what it is we have a receiving address, a transmitting address, a destination address, and a source address. Destination is the eventual destination on the LAN, not the IP address. It's the Ethernet address, MAC address. The source is the starting point where the packet starts. The receiver and the transmitters are the wireless part. On the wireless part, the transmitting station is TA and the receiving station is RA. So the receiving station will look at the destination and see whether it is going and then accordingly handle it. Right? If it is itself, then it will keep the packet. If it is not itself, it will send it to somebody. The four possibilities here. This is the most common possibility. We already discussed this one, right? Other possibility is that it is going from destination at the source address in this BSSID, or this is going to this destination from this source address, and so on and so forth. So there are several combinations possible, and this is the most common one, which is the one where it is going from some station via the wireless to the other station. These are the receivers and transmitters. But if it is just going inside the BSSID, then these three other combinations are used. But basically, so the idea is that four addresses are required because the LAN may be bigger than the wireless. And therefore, we need to know where the frame is coming from and where it is going, in addition to who is transmitting and who is receiving. So this particular frame is going from some station to some other station, and so therefore without going through the distribution system, which is the wired network. And so this is pure wireless. If it is pure wireless, then basically we have the destination address, source address, and the BSSID. On the other hand, this is coming from the DS and going to the wireless, and therefore it has only these two addresses, BSSID, the destination, and the original source address. This is going to DS, and so it has the final destination address and the BSSID. So BSSID is basically the access point. So it will go to the access point. Oh my God! See, the thing is, this BSSID acts as the receiving address for this frame because it is going to the access point, and from there it will go to the wired network. And here, the wireless and the access point acts as a source and the transmitting address, and here the access point is acting as a destination address, and so on, because it is not really going to the wired network at all. It is just going to the same place. So this is the wireless node A and B, and this is the BSSID is the access point. So the frame will be sent to the access point, and then from access point it will go to A or B. Right? If it is a access point based, if it is not access point based, then it will go straight from A to B in the ad hoc mode. So those are all different possibilities here, which are listed, and so this is the one that is receiving the wireless frame. This column. Okay, the column number 3. Now, 802.11 is a lot of standards, and you know some of them, 11A, 11B, but there are a lot more. So what I've done next is made a list of all the standards which are there and what they are about. We are not able to go into the detail of these, except just to know that they exist, and if you run into a situation where you need to know about them, then we have the URL to get to it. But anyway, we know 11A. 11A came out in 99. That is when it was being developed, it was called higher speed PHY extension in the 5 gigahertz band. 11B is the higher speed PHY extension in the 2.5 gigahertz band. There was something called 11C, which is bridge operation. So how the bridges will operate, and that is now completed and added to 802.1D, which is really the bridge standard. Then 11D is global harmonization, which is the PHYs for some other countries, such as Japan. They might have a different frequency available. 11E is the quality of service. So when you read papers about Wi-Fi, some of these numbers come up, and there are a lot of papers on 11E. 11E is quality of service, and obviously the academics are very much interested in it, and so there are lots of papers on 11E. 11F is the inter-access point protocol, doesn't exist anymore. 11H is the dynamic frequency selection and transmit power control to satisfy 5 GHz band operation in Europe. Okay, so they have some rules as to how you select the frequency and control your transmit power. So for that one is they have 11H. I is another famous standard. So everything that is famous I have put underlined. So we see A, B, E, H. Then there is I. I is the security standard. J is for Japan. K is radio resource measurement. M is for maintenance. N is the next one, which is higher throughput. This is the 11N. We will talk more about that. 11P is another famous one, which is for inter-vehicle and vehicular roadside communication. So they are developing an extension of Wi-Fi for cars. When you're driving in the car, you could get the information from the roadside post, which might have some information about what is the next exit, next restaurant, next gas station, and so on and so forth. That is P. Then there is R for fast roaming. Fast roaming basically going from one station, one access point to the next access point without losing the connection. 11S is the mesh network. 11T is the performance standard. U is the interworking standard with external network. V is the wireless management. Z is the direct link setup. AA, now they ran out of the letters A through Z, so now they come through AA. AA is video transporting on Wi-Fi. AC is very high throughput. AD is very high throughput in 60 gigahertz. So this one says very high throughput at less than 6 gigahertz, and this one is very high throughput at 60 gigahertz. So that's another frequency which is coming up, which is license exempt actually. So actually 60 gigahertz is not license exempt, but it is something that you can use after registration. So if you want to use 60 gigahertz, you go to FCC and say, well, I want to use 60 gigahertz at this address, and then from here to here, and that becomes yours. You don't have to really pay for it, but if somebody else is already using it, you may not get the permission. So this is the registration kind of thing. So anyway, so that they have a very high throughput in that 60 gigahertz band. Then we have AE for QoS management, and then for AF is for the TV white spaces. So what is happening is the TV stations are not using all their spectrum. Some of that spectrum can be used up by Wi-Fi, and so that is the white spaces stuff. Anyway, if you ever need to know more about these things, then here's the web page. By the way, this list is latest, up to date today, in the sense that some of these standards are very new, starting with AA, AC, AD. These are all very new. They will take few years to finish. So December 2012 is 2-3 years away, right? This one says PAR approved. PAR is the IEEE term for project approval. So PAR approved. So the project was approved on December 9th, 2009. So just last month or month before, this was approved, TV white spaces. All right. So are you supposed to know all this list? No, but actually the underlined ones we all remember. So if somebody said 11E, I remember that is the QoS standard. Somebody says 11I, I know that is the security standard. If somebody says 11N, we know that is MIMO standard. So some of the underlined ones are the ones that we just know for sure. And another popular one now is 11P, which is the vehicular standard. So we will now talk about those underlined ones little bit, which are really important in the 11 series. 11E is the next important one, which actually does the quality of service. Now in the 11E, what they have done is they have put priorities. Basically, so instead of having one priority, they have 8 priorities, but they have only 4 queues. So really there are 4 priorities in that sense. And what they have done is that the previous algorithm, which consisted of a beacon followed by the point coordination function followed by the distributed coordination function, now they have extended that to a little bit more complicated. And one thing about the point coordination function is, remember, point coordination function was for the contention-free period where we allocate you some bandwidth beforehand, so there is no contention. While it is in the IEEE 11 standard, 802.11, it is not implemented in any products, so it's more of a theory than practice, PCF. But since the standards, so basically in the new standards 11E, this DCF part and the part we just discussed a minute ago, that is the DCF part, that you have to declare you have to wait for nav to expire, then you have to wait for the diffs, then you have to do the back off. That has been extended to 4 different queues, maybe 8 different priorities. And so it is called hybrid. Actually, there are 2 parts. PCF has become HCF, which is hybrid coordination function, and DCF has become EDCF, which is the enhanced DCF. Okay. So now when you hear a beacon, after that there is a contention-free period, which is called HCF. After that there is an enhanced coordination function, and then there is another contention-free period, and then there is another enhanced coordination period, and so on and so forth. The reason they have to have so many is because the beacon interval might be too long, and these point coordination functions or the time critical functions may not want to wait that long, so they have multiple of these as opposed to just having one. So these are contention-free periods. Second thing, so basically this adds is, first thing it adds is that in this HCF, second thing it adds is direct link. So previously, if you had an access point, all the packets from A to B have to go from A to access point, from access point to B. Okay. Now if you got an equipment which is 11E compliant, then you can go from A to B directly. And so you just announce, even with the access point being present. In the ad hoc mode, obviously you could say I want to go from A to B, but in the access point case, everything went through access point, central point. But now you could set up a direct link. And third thing is that the frame bursting. Previously, every frame was followed by an acknowledgement. Now you could send a frame and say, I don't need the acknowledgement for this one. You get send second frame, third frame, fourth frame, and then you say, I need the acknowledgement. So you get the whole acknowledgement for all 4. So it's like having a bigger window than the window of one. And that is particularly helpful because with high-speed networks, the frames are very, very short, and so you don't want to get acknowledgement after every little frame. That is frame bursting and the group acknowledgement, and multiple priority levels. So now the multiple priority levels actually are by just extending all these parameters that we had before on the back of the CW min, CW max, why were we calling them BW min? I think this should be probably CW min. So for each priority we have a different CW min, CW max, and then we have the back off timer for each priority, and then there are this interframe spacing, which was your diffs, which is different. All right, and then the duration for each of these. So now basically, if you have higher priority, they have a smaller back off, and the lower priority have larger back off. So obviously CW min and CW max for a higher priority would be much bigger than for the for lower priority would be much bigger than for the higher priority. So higher priority may just draw a backup random number between, let's say, 1 and 3, while the higher priority might draw between 63 and 128, something like that. So that ensures that the higher priority frames get through first. And this is now called AIFS, which is the arbitrated interframe spacing. And so that is actually, there are 4 numbers here. This is smaller than the other ones. So when the medium becomes available, the higher priority weight less for what we used to call diffs. And the transmit opportunity is the duration and for which you can transmit, and each priority has a maximum size for which you can transmit. They don't want higher priority to be transmitting for very long, so then there is those number TXOP. And then there is a back off, 1, 2, 3, 4, those are basically your timers, which are random numbers. Alright? So the summary of this thing is that the EDCF is very similar to DCF, except instead of 1 parameter set, you have 4 sets. Alright? And higher priority traffic has to wait less than the lower priority traffic, as you expect. And so basically when a frame comes in, the station decides which queue it goes into, and once it goes into that queue, then basically it uses that parameter to sense the medium, to grab the medium. Now diffs is called what? AIFS. So the name for the diff has changed, and CW min and CW max are still CW min, CW max, and their values are such that the higher priorities have to have a lower CW, right? So their random numbers comes out lower. Now bursting is the next feature where you allow to send multiple frames. So you might send data, ACK, data, ACK, and then weight and all that. And there is a limit to how much you can do that at one priority, because you don't want to starve the lower priorities. So there is a maximum time limit before which you have to give up the medium. And the higher the priority, the lower the burst size, basically, so that not everything becomes high priority. Otherwise, everybody wants to be high priority. So voice and gaming has high priority but small burst size. Video and audio have lower priority. Video and audio have lower priority but larger burst size. So basically, priority and the burst size go opposite, right? And what is not shown here, actually there are 2 different things. Let me see. There are 2 different things. Frame bursting and gloop acknowledgement, they are 2 different things. Okay? 2 different things in the sense that what I have shown here is frame bursting. So I am transmitting multiple frames. However, each frame is acknowledged. So this is not a group acknowledge. Another alternative would have been to have multiple frames and then 1 acknowledgement. That would be group acknowledge. Right? So these 2 are independent concepts. With multiple frames, frame bursting, you get the permission when you do the RTS. In that you say, I want to send for the next 100 slot units. If you are allowed, if your TXOP allows, you can say, I want to send it for the next 100 slot units, and you could send 5 frames in that 100 slot units. And so you don't have to do TS, RTS, and CTS. So the frame bursting means that you do RTS, CTS once for a whole bunch of frames. And the group acknowledge means that you do 1 acknowledgement for a whole bunch of frames. Alright, so they're trying to minimize the overhead at both ends. The RTS, CTS overhead and the acknowledgement overhead. This is actually always a question as to how do you know what is this one. And the standard technique nowadays has been to use look into the other layers overhead, other layers headers, and basically by the port numbers. If it is an RTP packet which is real-time transport protocol, you look inside and then you do something and you figure out that this is high priority.
Doesn't that contradict the OSI letter though?
Yeah, so that is already contradicted. So one of the things that is happening is that for wireless networks in particular, you need cross-layer information, as we call it. So there is a concept of cross-layer coordination, where the higher layers would benefit very much by knowing that they're going over wireless or not going over wireless. Similarly, the wireless will benefit by knowing from the higher layers. So there is this thing about crossing the boundaries of the layers. So here are the 4 priorities: background traffic, best effort traffic, video and voice. These are the CW min, CW max, some value. The same value is used for these 2 priorities, but higher value is used but a different value is used for these 2 priorities. CW max value is given here. AIFS, these are the diffs value. So you can see the voice has the highest priority and their AIFS is lowest. And this is the TX up limit. This is the maximum nav that you could declare. And so this is 3 milliseconds, this is 6 milliseconds, and this is infinity. There is no limit on the background and the best effort. Alright, so we have finished the so-called 802.11e. 11e is the QoS standard. Just to summarize again, is the QoS standard, and it allows several new things. First of all, it allows 4 priorities. Then it allows multiple frames transmission by one RTS CTS thing. It allows multiple frame acknowledgement, and then basically it has more about those real-time traffic also. Again, we don't implement HCF, so it's not worth talking about. Hybrid coordination function was there in the first picture, but nobody implements it. So we just talk about the EDCF, which is the enhanced DCF. And enhanced DCF basically 4 priorities, which means we have 4 diff values, 4 CW values, and so on.